Hello, everyone. I'm here to present a slightly different view on mathematically structured functional programming. It's actually work that I've done a couple of years ago. The context of the work is a little bit because my work is actually at a big semiconductor company, and we frequently need to implement circular functions or trigonometric functions in our hardware and software. But I've been struggling to publish it, so now is the time to focus on it. I will first delve into some, let's say, basic facts about trigonometry that might be useful. Introduce some, let's say, abstractions that I find pretty new in this context. I will then proceed with a kind of a development of an algorithm that culminates in a nice implementation of inverse trigonometric functions that are actually competitive a little bit with what other people have implemented in mathematical libraries to some degree, some performance evaluation at the end. So let's start. Obviously, everybody knows sine and cosine and tangents and cotangents and how it behaves. It's monotonic, that is symmetric with various symmetries everywhere. So, and of course, the use is widespread. I don't need to prove that. I was going through a documentation of my house recently, and I found this permit. And then if you look carefully, you see here some trigonometric functions being mentioned by the construction builders, and also there is a square root. So this document, I think, proves the importance of this. Otherwise, my house would not have stood for more than 10 years. Yes, and of course, from my work as a software engineer now, systems engineer for NXP. So I'm doing quite some implementation of these signal processing algorithms, and it has a lot to do with complex numbers, with the frequency estimation, frequency correction of wireless signals. And in all those topics, trigonometry plays an important role. Obviously, FFT requires tables of sines and cosines and so on. For frequency estimation, you basically need to multiply with a sine or cosine function. So, what kind of questions do I want to answer by this talk? What questions did I focus in my paper? Do we need to really implement square root functions, sine and cosine functions, specifically each time? Can we not reduce one of them to the other? Then there is a question, of course, can we actually derive algorithms for inverse functions from the algorithms that we developed for forward functions? Can we avoid standard things like Taylor or Maclaurin series or pre-computed tables that are present in algorithms like Dyadic? And also, maybe a bit controversial question, can we actually enumerate all these continuous values that we have on this plot that I showed before of the sine and cosine? What is the context? The algorithms that I will be presenting, they work on Dyadic rationals, which are basically rational numbers where the denominator is an exponential value. So there is a k, and this defines actually the precision of this value. Dyadic rationals are very widespread in signal processing. Of course, fixed point numbers are frequently used in hardware implementations. They are actually Dyadic rationals. And of course, as I mentioned, these functions are symmetrical, so we can actually restrict the domain of the algorithm to actually focus on this 0 to pi over 2. And of course, by symmetry, we can then extend it to all other arguments. We are also, I'm also here factoring by pi over 2, this Dyadic rational. It simplifies, of course, many things. So, why do I want to avoid these explicit tables containing these values for hardware implementation? Actually, not only for hardware implementations, but also for software implementations. These are very problematic because of the need to allocate bandwidth to actually access all these values in this table. And for hardware, that would be a really big multiplexer, because when you look at how algorithms are mapped to hardware, they don't know beforehand what the value will be accessed, and they basically need to prepare for any access. This can be very, very expensive. So there's a kind of a trade-off that we want to do, and I think, yeah, by looking at tableless implementation of these functions, we can actually avoid it. All right, so yeah, let's start with real basics. So if we look at, let's say, some values of these functions, then we see that square root starts to play a really important role. And of course, yeah, half-angle formulas that probably everybody has used once in a while. They are inherently based on square root. So when I was working on this, I was thinking, well, can we not just iterate it? So if we look at the dyadic rational x over 2k, yeah, then basically it reduces to a value of x which is twice that, and then 4 times that, and so on. So we end up with this very complex continued radical expression, where there is a factor here that is being increased at each step of this iteration, actually by a factor of 2, so it's actually squared. And then you see basically that the signs that are defined by this expression here, that the signs are also following a certain pattern. So I was trying to understand what kind of pattern this is, and I came up with this table. So essentially, if you look at the signs and you encode the sign with plus minus, this column, then you will see that when converted to a decimal, you get a certain sequence. I call it SIG in the paper, and the sequence has some interesting properties that are quite important for, especially for answering the last question of mine. Yeah, when you look at it, you basically notice that it follows a kind of a binary tree pattern, because you start at the middle, and going deeper, you basically dissect the interval depending on where you go, and the sign depends on where you go, left or right. So if you go to the top, then it's a plus. If you go to the bottom, it's minus. And obviously, these functions, the values that you see here, they are monotonically decreasing or increasing. I mean, from top to bottom, they are decreasing because it's a cosine. So basically, yeah, at the top you will see all pluses, and at the bottom you won't see all minuses, because every time you have a minus and a minus, then the value becomes larger actually. So there's an interesting kind of property of the sequence, and I was trying to understand it, what the sequence is, and basically I did a plot of it, of the stick values in decimal, and immediately you see, well, this is the kind of fractal pattern that appears, and this fractal pattern is in fact a non-fractal pattern, because I was trying to find it in the online encyclopedia of integer sequences, and I succeeded. But let us first look at how I define it, the sequence formally. So it is basically defined here by this algorithm. It's, forgive me for using Julia, because Julia is nice for doing plotting and doing all kinds of mathematical operations, and it's quite close to languages that I used in my company. But I think the pattern is quite clear. So basically, we are maintaining a kind of an accumulator. It's called here as S, which is being extended by each iteration of this loop, and essentially it is looking at the amount of positive signs in the sequence, checking if it's odd or negative, odd or even, and depending on that, it generates a new sign. So if you try to simplify it, you end up with a function like this, which is basically like proving that this is a fractal sequence, because it has itself as a subsequence. And yeah, with further simplification, it becomes this, which shows basically some yeah, some functional programming patterns that are useful here. When I plotted this the sequence in Julia with all the duplicate values removed, you get a plot like this, and this is immediately something recognizable as a gray sequence, which is present in the online encyclopedia of integer sequences. But the repetitions, the fact that it's fractal, this one is due to the sequence which modulates the gray sequence. In this case, it is related to Dyadic fractionals also, but also in OEIS, it is called the Kimberley paraphrase sequence. So the fact that my sequence that I defined a couple of slides back is actually the same as this sequence actually can be easily verified by this expression. So by basically modulating gray sequence like Kimberley paraphrases, you get back the exact same sequence. All right, so after this, I decided, well, let's use Scheme. Scheme is a nice functional programming language, very simple for me to understand. And I started basically with basics, with the square roots. So how do we implement square root in Scheme? Yeah, this is a well-known algorithm, but to get any kind of performance out of it, well, you need to use this special fixed point operations and so on. So I decided, well, let's simplify it a little bit. This will not be used really essentially here, but it's just a nice syntactic simplification. So basically, I introduced kind of typing annotation to functions to get rid of this annoying suffixes. All right, so how do we go about actually implementing our functions? So because this is a continuous radical that we need to implement, I think it's natural to use a continuation passing style for it. So basically, the evaluation it receives inside out, so from the deepest term in this continuous radical, and basically when we build this, we build a chain of nested closures that are being evaluated in the end. It's a bit similar to what I believe Olivia Dunn calls Dyadic pattern. Of course, this is not very efficient because there are all these closures being created. It's not very efficient. So what I decided then is to actually take another look at this problem. So I had a first key insight. So basically, the signature defines the signs of nested terms in the continuous radical expression. Well, let's look at it at actually the encoding of our target value. Let's have a look. Can we use this fact to actually improve the performance of the system? And it turns out, yes, we can. And in fact, if you look at these values, the values of this sequence at different depths, you actually notice that it does actually enumerate all values. Only you need to know that because at all the terms which are at all the arguments which are 1 over 2 to the k, or 2 to the k, then the value is 0. So we need to do something about the fact that it's not injective to the natural numbers. But this will be addressed later. So if we do defunctionalize this function, the previous implementation into another one where we basically split the relation into parts which builds this signature, and in the end we finally applied it to get our value of cosine, then it's already an improvement. However, in this function we still have a problem that this decreasing factors of f, they become very small, vanishingly small. And at some point, you can no longer get any improvement in the precision of the algorithm because the f will become 0. To solve this problem, I actually had to do various optimizations, so like simple rewritings to get rid of control structure as well, and also in the apply function, and as well as in the main function. So And to get rid of the problem of this vanishing factor f, you can apply really a simple observation, saying that, well, if we take this original expression of this continuous radical and we just count it here, we put the count here, but we multiply it with 4 over there, then eventually all these diminishing factors will be cancelled, and we end up with a very nice expression which only has, let's say, natural numbers. Right? So I use that to actually simplify it, and yeah, my second key insight, I have actually adapted this signature sequence as well. So basically, by just prepending 1 bit in front, you can actually do both operations at once. You can keep track of the signature, get the depth of this dimension, and you can also get this injectivities. Basically, you can take any value from the sequence, and it will correspond to a certain value of cosine corresponding to that parameter. And it's also reversible, because now there is basically one-to-one corresponding in those values. And of course, yeah, if you look at it carefully, it still has this kind of visible structure here. So actually, you can just enumerate all values by looking at all odd elements of the sequence at each depth. So basically, it's 2, 4, 5, 8, 9, and so on. So this will give a unique sequence of unique integers, which basically enumerate all of those values. So how do we? How did I finish with this? So basically, I applied all these control optimizations, all this representation optimization, and then we get this very nice function, which I think is quite simple, and it looks like it could also be used for implementation of the reverse. And that was my next target. But before that, I also wanted to actually implement a lot of functions as well that are useful in my work. So actually simple to see that sine can be simply derived from the same equation. So the only thing you need to do is to swap the sign here. So if there is plus here, then it will be a minus here, and then the end result will be a sine value. And similarly, yeah, from trigonometry, you can find expressions that will map the value computed like this to tangent or cotangent and so on. So that's a simple generalization that extends the domain to the whole reals, basically, or rationals, I should say, dyadic rational. And yeah, let's look at how I implemented inverse functions. Well, of course, the function is monotonic here, so we can just do binary search here as well. And this was the first, let's say, naive attempt to do it. So basically, just calculate the target value here by applying the previous slides, and just search for it. So depending on whether it's less than target value or greater, we add signs here to the sign sequence that I explained before, and we add to this rational that will be the result of this function. But this is not very efficient, of course, so I had to do something there. I went back to the basics, to this continuous radical. And from this one, you can actually immediately see how to invert it. You have to basically do the doubling of the argument. Then you apply a square, right? And then you see this expression here. Then you subtract 2, and then you can understand whether this is positive or not. And if this is positive, then the sign is 1, and otherwise it's 1. So it's basically like I'm doing all these nested expressions one by one. And of course, a key insight, why can we use this for any kind of inputs, even inputs that were not generated using the procedure that I explained before. That's exactly because our mechanics is one-to-one. So there will be a number at some point which will correspond to any real that we give Yeah, the procedure is very simple. I think it's all in the paper. So if we use that and improve our loop, basically, then we get back a function that we can find the Dyadic rational based on the real input at any depth. Similarly, we can implement obviously other inverse functions, arc sine, arc tangent, and so on. So yeah, let's look at evaluation. Last 3 minutes remaining. So if we look at the time that it takes to evaluate those inverse trigonometric functions implemented this way, then obviously it's linear depending on the number of iterations that we do. If we look at the error, then it shows a quite decent performance. Of course, some functions are using the reciprocal functions, so they are letting out earlier. In terms of the error that we observed, let's say, benchmark implementation or library implementation of those functions. And the important feature is actually this one, because it shows the speed up obtained by using this implementation instead of the baseline. So there is, of course, yeah, at some points it becomes less performant, but there is still a quite large domain of values of precisions for which this implementation is more useful. So let's give some answers to these questions that I mentioned initially. So I think for this kind of functions, we have many square roots. So if you implement the square roots in hardware, for example, then this will give us also a very nice implementation of forward trigonometric functions. We don't really need to implement this inverse function specially, because we can just follow this procedure, and just with squaring and doubling, we can recreate the signs and in effect recreate all this Dyadic rationals that I used in the input. We can avoid tables here. There are no tables involved here, and also no evaluation of expenses here. So potentially, yeah, we can do all of the things. And yeah, similar to Cantor's enumeration of rationals, we can also enumerate all the circular values this way. Yeah, to conclude, I was implementing this, and I found out that with the software implementation of square roots, these implementations are not competitive for forward functions because of the square root, of course, but for yeah, inverse functions, it is quite competitive, and I think it's a nice example of how this kind of algorithms can be implemented, and I think it also shows that using functional programming for this, it really helped, because I could actually see at each step of the development of the algorithm, yeah, how it relates, let's say, to the historical development of functional programming, and how all the techniques actually used and advantages. So I would like to, yeah, thank you.